Take it away.
Hi, good morning. My name is Sibo Wang. I'm a grad student from the University of Illinois. Specifically, I'm from the Department of Natural Resources and Environmental Sciences and the National Center for Supercomputing Applications. And today, my presentation will be on using CubeSat, specifically PlanetScope observations as a part of interoperable data collection. So what we really want is that we're a lab, my lab is primarily doing agricultural analysis. Me, for example, I do crop modeling. So what we really want is to integrate all the observations we have, be it PlanetScope or MODIS Landsat, and integrate them into one single high-quality surface reflectance data set that is ready for our use. So what we really want ideally is a data set that is cloud-free, gap-free, high resolution, and high revisiting frequency. We want such a data cube that also has consistent measurement, if only that exists, right? So it doesn't. So our lab is trying to work our ways around those problems and approximate something that we can use. So in a way, we are really a client of true analysis-ready data because like my lab, actually, we really don't care how which sensor the data comes from or how atmospheric correction is conducted. So what we are doing to solve those problems include a little bit of multi-sensor fusion, a little bit of cloud mask. We developed our own cloud mask, and also a little bit of geolocation correction, and finally spectral correction. And today I'm going to just give you a brief introduction to our work in these topics. The first one will be fusion. We developed our own multi-sensor fusion algorithm named STAR. It was led by one of my fellow grad students, Yunan Luo. And it is a fully automated algorithm, so it is feasible to run it at large scales without having to manually select, for example, which scenes to use or to manually tune every single parameter. It has a novel gap filling algorithm that handles artifacts such as those gaps in Landsat 7 and cloud shadows really well. And it generates data at daily frequency. Because the rationale of this algorithm is basically to combine the high frequency of sensors like MODIS with the high resolution of other platforms. Of course, this daily frequency product is probably only reliable for agricultural uses because the surface reflectance of a cropland is, well, it is reasonably smooth. Whereas if you're using planet data for example, counting how many cars there are parked at Walmarts, it's probably not a good idea. The first version of this product incorporates MODIS and Landsat, so we have 30 meters resolution, daily frequency data cube. And this algorithm is not limited to just two data sources. We can just overlay one product on top of another, hence the name STAR. So currently we're working on including Sentinel-2 data as well, which is reasonably straightforward. This way we get to 10 meters resolution, and eventually we're going for 3-meter resolution with the inclusion of PlanetScope data. Those are two workflows from Yunan's paper. So basically we have a really good gap filling algorithm that's robust for any kind of cloud fraction. and then we use the MODIS N-bar data to capture the general time series trend, and use Landsat to capture the higher resolution spatial detail. Here's a demo of the algorithm in Champaign County. So on the left is the RGB color. On the right is GCVI, which is a kind of vegetation index. And this is for the summer growing season of 2017 in Champaign, Illinois. As you can see, there's very little artifacts. You can't see the Landsat 7 data gaps, and very little cloud and cloud shadows. Another thing we are working on is that we are building our own cloud mask, and this is a two-part project. First of all, we are trying to build a generic deep learning powered cloud detection algorithm, and building on top of that, we are working on a reduced version that is tailored for PlanetScope. So for those of you who don't really have a background in machine learning, here's a little bit about convolutional neural networks. So basically, what we are doing is that we have a bunch of filters, things like the little matrix in blue over there, and on the left we have the actual image. So what we are doing is that we are moving that filter across the image and use those little weights to multiply the values in the image to achieve a somehow processed value of that pixel. And there are different filters. For example, this one over here is good for blurring the image, because we are basically, for each pixel, we are taking the average of the nearby pixels. For this filter, it's good at detecting the vertical boundaries of foreground features, such as the dog. It's probably not very clear on this slide, but so anyway, the basic idea is that maybe somehow there is another filter that works really well on satellite images in such a way that, given a satellite image, we get a cloud mask. That's a basic idea. Of course, it's a lot more complicated than that. So we have a neural network of doing that. So what happens here is that it's very hard for people to figure out that somehow let me put a 2 over here and a -1 over here to get such a filter. So we want the neural network to then learn those weights by itself, and there's a whole bunch of those convolution layers. So that's a basic idea. And what we are doing here is that, as opposed to traditional cloud masks that are used for sensors like Landsat, such as FMask, they rely on hard-coded thresholds and empirical rules that is basically a human-designed decision tree. And frankly, it works really well for such a empirical method, but it also has a lot of problems like the misclassification of cloud as ice or snow, and the low accuracy for thin cirrus or cloud shadows. So what we are doing here is that we use novel deep learning approach for cloud detection. It's a work led by another grad student in my group, Xu Ke. And even after that, we have an additional problem for sensors like PlanetScope, because PlanetScope only has 4 bands, so it can't really use the same algorithm as, for example, Landsat uses. So what I'm working on is to use transfer learning to approximate the results of such a fully developed cloud detection algorithm using only RGB and near-infrared bands. And if you think about it, we as humans can almost perfectly identify clouds on an image even only with RGB bands. So I do believe that there's sufficient information covered in just RGB and near-infrared bands. Another topic would be geolocation co-registration. It's probably the most boring one. We just take a bunch of type points or feature points and figure out a global shift pattern. And on the right here, you can see, and we do that across resolution levels. So on the right, you can see we have 30 meters Landsat image on the left and 10 meter Sentinel-2 image on the right, and they are perfectly aligned, whereas in the raw images, the streets here, there is a mismatch. Finally, another important, very important topic will be spectral correction. And we're using a lot of sensors. We're using MODIS, we're using Landsat, we're using Sentinel, we're using PlanetScope, and obviously they have very different, not very different, but still different spectral responses. And that's because they have different sensors that are configured in different ways. And the algorithms used to generate those data have different biases. And we have different band definitions. We have different local overpass time. So for our lab's purpose, we don't really care which spectral profile is more accurate all that much. I mean, we'd like there to be as much information as possible in the data, but we don't really care exactly at which wavelength does the near-infrared band start and ends. We don't care about that kind of information. We do, however, want a consistent spectral response. So if we are working on, for example, a Landsat image, and I have another PlanetScope image, we want it to be the case that both images are comparable. They have different resolution, sure, but we'd like them to have the same spectral profile. So therefore, we corrected everything else, Landsat whatever, Sentinel-2, PlanetScope to MODIS and bar, because that is a widely used and well-trusted surface reflectance dataset. So what happens here is that we have our fusion, we have our stair fusion results on the left, has 30 meters resolution. It already has the same spectral profile as MODIS and bar. We have the CubeSat data over here, and we basically take the distribution of, we basically take the distribution of the stair output and force the PlanetScope data in such a way that it shares the same distribution as the 30 meters stair product. And if you look at the zoom in of the 30 meters stair results and the processed PlanetScope, you can see that they have different resolutions. This one is 30 meters, this one is 3 meters, but overall the color, the spectral profile is the same. And they have, if you plot the histograms in each band, they look almost identical, as shown in the solid lines and the thicker dashed lines. We even developed our own atmospheric correction algorithm that is purely based on inferring distribution from external data sources. And that is before the surface reflectance product from Planet was released earlier. And because we are using Planet data for very specific application, that is to study, for now our lab is primarily studying corn and soybean because we're in Illinois. So because of that, we can actually infer some more information from the crop cover type. So we develop a land cover specific outlier detection algorithm that basically uses our existing knowledge of how that time series of that corn field should look like to detect more spikes that are otherwise harder to identify. And it leads to better quality of the QA mask. Finally, I'd like to give a special thanks to the Blue Waters supercomputer at NCSA. It provides great computational power and storage capacity and allows us to work at fine resolutions, even at large scales. That's it from me. Thank you.
Great, thank you so much. And I think we're getting back on track with time too. So I think Rin, is that your laptop? Okay. So.
I don't know which one was there.
Sure.
I think so.
Hello, thank you for coming here. My name is Arin Jumpasut and I work at Planet, and I'm going to talk about interoperability between PlanetScope, RapidEye and MODIS TOAR products, specifically the radiometric side of it. And I just want to quickly acknowledge my my colleagues, Alan Collison, Gina Lee, Josh Greenberg, and Director Ignacio for their help in all of this. So quickly about why this is necessary. So I think most studies these days combine data from different sources, and even if the satellite is well calibrated and precise, like Landsat 8 or Sentinel-2, extra processing is always needed to try and harmonize them. For example, the multiple projects to harmonize Landsat 8 and Sentinel, like Sen2-like, as well as the harmonized Landsat Sentinel-2 product. And this lack of normalization poses a challenge to these studies. And in calibration, this might be done using a spectral band adjustment factor or something, but that requires knowledge of what you're imaging to calculate these factors. And so this study is just looking at one way to normalize it for certain types of land cover class. And so why this is necessary? So just taking a field and calculating the raw NDVI products between RapidEye and PlanetScope, if you put them together for a simultaneous crossover, you can see a slight mosaic artifact in NDVI where the values are not continuous between the two satellites. And looking at time series as well, you can also see this effect where they don't align. And one possible reason is that the spectral, the bands are quite different. So this is the relative spectral responses of the RapidEye satellites and the Planet satellites. And you can see that, for example, the Planet green band has some contributions from the same kind of wavelengths as RapidEye blue and red. And again, for MODIS, the bands are also quite different to each other. And so my study concerns a more larger scale regional analysis of a comparison of simultaneous crossovers, so that we can try and correct on a larger scale to try and correct some of the bias from the data set, but it might still leave some degree of variance within it, so that you correct the bulk of it, but there will still be some local differences between the two sets. But this will be like a first step as a broad regional scale analysis correction before moving on to a local per pixel correction, which Gina Lee will talk about later on. For my study, I used about 60 AOIs in the Midwest of America, and I looked at the last year's growing season in the summer, so between May and October 2017. And I looked at I used PlanetScope, RapidEye, and MODIS top of atmosphere reflectance data. So I didn't use surface reflectance data from MODIS or anything, so that we could treat the atmospheric correction as a separate step and look into the effect of that separately. And then at the moment, I'm just looking into per band linear corrections, so just gains and offsets. So first of all, how do we define a simultaneous crossover event? So we try to give quite a flexible definition of 2 hours as the maximum time difference between the two collects, so that we can try and gather as much data as possible. Since RapidEye can vary its view angle, we try to minimize the effect of that by only selecting scenes which have a view angle of less than 10 degrees. And we do have some quality filters on the pixels, but we didn't filter for clouds or cloud shadows. So the data is slightly messy, but we hope that there's enough data that we can get the trends. So for each of the simultaneous crossover events, we split up the analyses into subtiles of 2.5 by 2.5 kilometers. Ideally, you might be able to use some homogeneous fields or some kind of smaller kind of unit to do your analysis. But since we tried to do this at large scale and automated, this seemed like a suitable compromise of subtile size for computational complexity, as well as trying to keep the subtile areas manageable. And so for each subtile, we only use the joint mode of the distribution of pixels between the RapidEye and the PlanetScope satellite to summarize what the reflectance value for each of the bands is for that subtile. And this was an attempt to kind of force some kind of homogenization onto the dataset. So as I mentioned, we used about 60 AOIs. So within that period, there was about 1,103 crossover events, and then and that included about 130 different PlanetScope satellites. And as I mentioned, there's no filtering for haze or cloud shadow. And so these are some of the results of the raw PlanetScope reflectance against RapidEye reflectance on the y-axis. For each of the different bands. And there's a clear linear trend in the data, which you can fit to. And yeah, if you calculate that fit and reverse it, you can you can get some corrected results from it. And how this affects the vegetative indices is like so. So it improves it slightly. So before, the vegetative index might be slightly off the one-to-one line, and since within the bands we're forcing them to the one-to-one line, the vegetative index reflects that. And so these are just an example of some of the gains and offsets that were calculated from before. And we did a similar thing with MODIS. And since we corrected the PlanetScope to RapidEye, we decided to correct the MODIS to RapidEye just so that for ease of use. And we used the MODIS top of atmosphere product, which was quite interesting. It was the Mod 02 HKM product, which is a 500 meter per pixel product. And it's a raw swath product. So we had to do some corrections to get it to a similar state as the other data, which I guess is similar to, and we get, and using a similar process as before, we can calculate the linear fit and reverse it out to try and correct it to a RapidEye equivalent. The green and the blue data for this data set was actually quite limited in the dynamic range. So it was a bit more difficult to get back good fits for them, but the red and the NEO-IR work okay. And again, looking at the effect on the vegetative index, you can see that it's closer to the one-to-one line. And again, these are some of the gains and offsets found. So we looked into, we started looking into some validation for this process. So here's a field again from before, and then here's the raw results and the corrected results, and after the correction, the results for all of the constellations are slightly more aligned, and can the time series seem to make a bit more sense. And again, this is the raw results for that field, and then this is the corrected results. And I'm not sure how clear it comes out, but hopefully it's a bit more, there's less of a mosaicing artifact when you look at them. So we looked at the data set again in a few different ways. We wanted to see whether there's any difference when you looked at the data between the different flocks that we launched last year. So Flock 2P is a set of satellites which we launched in late 2016, and so they have the most amount of data. And Flock 3P is a set of 77 or so satellites that we launched in February, and Flock 2K around 40 something in August. And you can see that we have a lot more data from the Flock 3P because of the sheer number of satellites compared to Flock 2P. And we only started getting data from after the launch, obviously, for Flock 2K. But you can see a kind of a rough idea of how frequently we got crossovers for each of the flocks. And then we looked at the effect of the correction on each of the flocks individually to see if there's any differences in effect on any of them, and there wasn't that significant a difference. So that was quite reassuring, because it meant that we could use the correction on any of the satellites without having to do a per flock correction. And again, we wanted to look at the correction over time throughout the growing season, and this is just the number of events throughout time. And you can see that although the dynamic range of the NDVI measurement changes through the growing season as it goes up and down the scale, the actual gradient of fit seems to be quite stable around 1, although not quite hitting that all the time. And finally, we did a little bit of an analysis between the AOIs to see if there's any significant geographical differences between the correction. And on a larger scale, there doesn't seem to be too significant a difference, although we need to look into it a bit more. But within an AOI on a local scale, each of the subtiles, looking at each of the subtiles, if you had a purely agricultural subtile, on the whole, the fit seemed to be a bit better than if you had a mixed-use subtile with the city, for example. So, as a conclusion, we're quite confident that this correction can work quite well within the limitations of looking at agricultural areas over the summer for the Midwest region of America, and that the per-band linear corrections are quite okay for this situation. But it needs to be expanded and look into other agricultural areas. For example, California might have slightly different behaviors, and Europe as well. We can expand that study, and we can look into this year's results as well. That's everything. Thank you.
Thank you, Arin. And if we get Arin and Sibo up at the front again for another QA session, that'd be fantastic. And Sibo, I'll start it out. I was just kind of curious when you were talking about your machine learning with for the cloud detection. Could you talk a little bit about what size training set you had and how you labeled that, and And were there more than, was it just basically cloud, no cloud, or did you have other categories in there?
So it is an ongoing project, and there's actually another person in the lab working with me, and he was working on the full cloud detector while I was working on the transfer learning on for PlanetScope data. I believe he's working with about somewhere on the order of magnitude of 100 Landsat 7 scenes, Landsat 7 or 8 scenes, whereas I was for my project, I actually had a very specific need for that PlanetScope cloud mask. So I only trained on a couple dozen scenes in one specific area because that's how I wanted. So spatially not very generic, but luckily the algorithm itself, I believe, is generic. So like worst case, you just train a separate model for each area of study. And the volume of training data is somewhere around 100 since.
Okay, thank you.
Thank you.
Both great presentations. For the calibration one, did you do any investigation into the impact your time window had on your correlations? For example, 1 hour versus 2 hours or any of that?
No, we haven't actually. Yeah, that's a good point because there's quite a lot of change between that. For the initial study, we wanted to try and leave the time window as wide as kind of possible so that we could get as much data. But that's something that would be interesting to look into, actually, yeah.
Very nice presentations. Thank you both. This question's for Arin. You mentioned it, I think, kind of near the end of your talk in passing about using sort of multiple bands. So you've got this problem where you have different sensors with different bands,
Right.
and you've essentially found the closest band in sensor A to sensor B,
Right.
and you've done the correction that way.
Right.
But you mentioned that you could use all the bands in sensor A,
Right,
and your
right.
correction would be like a matrix.
Yeah.
Can you talk about that and what more you would get from that, and how much more work it is, and et cetera, et cetera?
Well, I think that would be like quite a logical next step in the study. And as you could see from the RSRs, there was some contribution for like RapidEye's other bands in all of the bands actually. So although it would definitely help a bit, I think it would definitely be something which would be interesting to look into. I think for the initial study, it was kind of we justified in going with the per band linear correction because although there is some contribution, like for the near IR band, it's quite minimal. The differences between RapidEye and PlanetScope, and although the red is still quite different.
Question for Sibo. Related to this question, what was your methodology for doing the spectral normalization to Landsat? Was it also per band linear corrections, or was it fancier?
We tried a little bit of both. We did try taking a bunch of sample points from days where the observation time was close and the geolocation was close. The one from my presentation was using CDF correction, so we basically forced the two cumulative distribution functions to be the same.
Cool, thanks.
Any other questions? Going once, going twice? Oh, here we go. Sold.
For Sibo, you said that Planet needed a different cloud algorithm, so you did this transfer learning.
Mm-hmm.
Would it require less transfer learning to transfer from Landsat to Sentinel? Is there a way to get a cheap conversion of an algorithm that has been trained on Landsat data onto the Sentinel data, other than simulating Landsat from Sentinel?
I suppose so, because the spectral coverage of Landsat and Sentinel are closer than from Landsat to PlanetScope. they also have more similar resolutions, but we haven't tried that yet. That's a very interesting next step for us to try. Thank you.
I walked slowly to make sure there wasn't anybody else making a move. I don't think so. Arin and Sibo, thank you very much. And I think we actually ended up a little bit early. So I guess we'll reconvene here at 1 o'clock. I believe lunch is already out there waiting for everyone. Thank you, everybody.